We saw some formulas in a previous video for finding Laplace transforms of a small library of functions. What they didn't give us was how to find the Laplace transform of a piecewise defined function. Here we have f of t is equal to 2t plus 1 for t between 0 and 1, inclusive at 0, and it's 0 when t is greater than or equal to 1. We're going to use the definition to find the transform of this function. The function is defined in two pieces depending on the value of t. When t is between 0 and 1, the 2t plus 1 definition is in play. And when t is greater than 1, the function is 0. The definition of the Laplace transform of f of t is the integral from 0 to infinity of e to the negative st times f of t dt. But since f of t has those two definitions, what we're going to do is use two integrals. One goes from 0 to 1, and the other goes from 1 to infinity. E to the negative st is in both of them, and in both cases we're integrating with respect to t. And on the interval from 0 to 1, our function is 2t plus 1. On the other interval, our function is 0. Good news. Even though the integral from 1 to infinity represents an improper integral, it's a definite integral, and the definite integral of 0 is 0. Integration by parts is going to give us negative, the fraction is 2t plus 1 over se to the st minus 2 over s squared e to the st, and that's evaluated from 0 to 1. I encourage you to confirm that using integration by parts. Evaluating these at the upper limit of 1 and the lower limit of 0, and then subtracting and simplifying, is going to give us 2 over s squared times the quantity of 1 minus e to the negative s, plus 1 over s times the quantity of 1 minus 3e to the negative s. You'll notice I factored these, I grouped them according to the power of s. We could have, if we wanted to, group them according to the exponential term and then the non-exponential term. This is just one option. We're going to use the definition again, and we're going to find the Laplace transform of e to the negative 2t minus 5. Well, it's the integral from 0 to infinity of e to the negative st times e to the negative 2t minus 5 dt. What's that negative 5 doing for us? Hey, it's e to the negative 2t times e to the negative 5. That e to the negative 5 is just a constant. It can come out of the integral. What we're left with is e to the negative quantity s plus 2 times t dt. That's going to give us e to the negative 5 over negative s plus 2 e to the negative s plus 2 times t, evaluated from 0 to infinity. Evaluating infinity in place of t is going to give us 0, and then evaluating 0 in place of t is going to give us a factor in the denominator of 1. Since we're subtracting that lower limit, we get e to the negative 5 over s plus 2. If we wanted to dot all our i's and cross all our t's, we might note, well, s has to be greater than negative 2, but again, like for our work, we're not really going to care what s is. Next up, we're going to use the theorem, that was the one that had the formulas, to find the Laplace transform, first of t squared minus e to the negative 9t plus 5. Well, we can write it as one big Laplace transform of t squared minus e to the negative 9t plus 5, or you can write it as three little ones, but I'll just leave it at this. And according to the formulas that we had in the theorem, the transform of t squared is 2 factorial over s to the 2 plus 1. So that's going to give us 2 over s cubed minus the Laplace transform of e to the negative 9t is going to be 1 over s minus negative 9, and so 1 over s plus 9. The Laplace transform of 5 is the Laplace transform of 5 times 1. That's 1 over s. So we're going to multiply that by 5. We get 5 over s. In this list of transforms of basic functions, we do not have a cosine squared of t. That's the next one we're going to look at. But using a power reducing formula, the cosine squared of t is 1/2 of 1 plus the cosine of 2t. Rewritten, that's 1/2 plus 1/2 cosine of 2t. The 1/2 will transform to 1 over 2s. And then the transform of the cosine of kt is s over s squared plus k squared, and in this case, k is 2. So we've got plus s over, now for the cosine, we have this s squared plus 4, and there was a coefficient of 1/2, so in that denominator, I'm going to put 2 times that quantity of s squared plus 4. And these are our transforms. Notice, if you were to let s go to infinity, every one of these would go to 0. And then further notice that we started with functions of t, and when we transformed them, we ended up with functions of s. This was just an introduction to the transforms. The utility of the transforms for solving differential equations will become evident starting in the next set of videos.